New center of inversion using Gauss-Newton. And I'm going to apply the center of inversion. Go back. Very fast. Very fast. If you want to parallelize this, is even parallelized. Okay. So that's it. Good. Now for the fun part. You guys ready? So if you're a geometer, one thing you don't like about this, maybe there's actually a lot of things you don't like about this. I hope there's just one, because that's the one I'm going to address. What we're doing here is fundamentally extrinsic. We're sort of taking points on the sphere as embedded in R3 and taking their weighted average. And yet, the stuff we're talking about is somehow really intrinsic. It doesn't really depend on the embedding. It just depends on the metric on the surface. So if you're unhappy about that, I'm happy. If you're unhappy about something else, then that's okay. Let's take a look at what's going on here. Right? So what did we show? We showed that if you have an inversion that you're applying in direction C, what it does is it flows a point P along this vector field, the projection of C onto the tangent plane at P. That's how point P is going to move under this inversion. Let's write this out a different way. What is this thing? What is this vector field? Well, I can take the function in R3, for example, that just says take the dot product with C. It's a simple function, it's a linear function. It's a linear function in R3. I can restrict it to the sphere. The restriction of that function to that sphere is exactly the projection of C onto the tangent plane of the sphere. I can also look at the second part, right? We talked about what it means to be centered. Well, we said centered means that the center of mass is at the origin. The weighted center of mass, weighted by the conformal factors. What's another way of saying this? Well, another way of saying this, if I take my conformal factors, scale factors, and I integrate them against x, the function x, I get 0. If I integrate them against the function y, I get 0. Integrate them against the function z, I get 0. In fact, if I integrate them against any linear function, they're 0. Or equivalently, that if I look at these scale factors, their projection onto the space of linear functions vanishes. And what you've noticed is there's something funny going on here. There's this linear here and a linear here. And this is no accident. Let's make the general statement. The general statement is if I have a space of functions on the sphere, let's say they don't have constant functions, so that I don't have to worry about gradients that are everywhere 0. I can look at deformations that are characterized by flows along vector fields that are gradients of functions in the space. Infinitesimally, let's look at the set of deformations as such. I can also define what it means to be centered. I'm going to say it's centered if the projection of the conformal factors onto the space of functions vanishes. And then what I can do is I can say, okay, we define a centering energy by taking our scale factors, projecting them onto this space, and looking at how big they are. And that's something we want to minimize by allowing ourselves to deform by flowing along these vector fields. So the theorem is that the gradient of the centering energy vanishes if and only if the stress vectors are centered, and the proof is identical. We show that the Jacobian of this mapping is symmetric positive.
So this is for the space of linear function or any space?
This is any space of functions. Any space of functions.
Okay, so centered in the sense of, so it's centered
with respect to projection onto that function space. So there's this coupling between the deformations you are allowing, which are deformations that are characterized by gradients of functions in the space, and centering, which is notion of projection onto the space. There is no analogous uniqueness proof. That I don't have. I don't think it exists. It sort of depends, I think, on the curvature of the space of differential maps or deformations that are characterized by these vector fields. So you need to have some better sense of that. But certainly existence. So let's go back to this extrinsic versus intrinsic question. Right? We're doing centering with respect to Mobius inversions, right? What do we do in this case? Well, in this case, what we showed is we took the specific case where the space of functions we're interested in are linear functions. Inversions correspond to projection along the gradients of linear functions. Centering means the projection on the linear functions is 0. Well, what are linear functions restricted to the sphere? Those are spherical harmonics. These are first-order spherical harmonics. So already we're now getting a characterization that is intrinsic. First-order spherical harmonics, they are the eigenvectors associated with the Laplace-Beltrami operator, completely intrinsic object, linear operator on the space of functions.
But it's intrinsic to the sphere, not
Yeah.
to the surface of
Yeah,
the
intrinsic to the sphere. Right. Yeah, intrinsic to the sphere. Correct. That's right. Exactly. No, but before, when we were taking the center of mass, we're taking center of mass points on the sphere, and that was extrinsic to the sphere. But really, what we're showing here is that this can be done entirely intrinsically. And it's also sort of, right, we're taking linear functions, gradients of linear functions. These are, since these are sort of the first non-trivial eigenvectors of the Laplace-Beltrami operator, these are the smoothest vector fields you can come up with. Right? In some sense, they are the eigenvectors of the Laplace-Beltrami operator with the smallest eigenvalue. You can look for less smooth vector fields. Right? You can use higher order spherical harmonics. And so here's an example. Right? So this is what we had before. We had a mapping of our shape to the sphere. We had a conformal parametrization. Then we did Mobius balancing, or centering, with respect to the just the first order term. And since those correspond to inversions, those will preserve the conformal structure. But if we look at higher order harmonics, we are now characterizing deformations that are not just conformal. They allow us, give us more degrees of freedom with which to distribute the mass. So the mass is more uniformly distributed at the cost of angle preservation. So this gives you a trade-off.
To compute these numerically, you are doing so same thing on the gradient descent of the.
Yeah. Exactly.
Okay, with the parametrization of so you take the harmonics of the first.
This is let me try and, the only difference is, over here, I get, when I do sort of apply the algorithm that I was talking about, I get the center about which I want to do the inversion. Over here, I don't get a center, I get the vector field that I want to use to advect. So I somehow need to move things, I need to flow things on the sphere. Now, that's not characterized by an inversion, but I can still do flow. I can still move things in infinitesimal or small distance along geodesics that are defined by this vector field that will try and move things towards a more balanced state. So the implementation is different. Now, computing geodesics on a sphere is not hard, right? Because you just know that they're...
So you are dynamically evolving between the random descent.
Exactly. So the implementation is slightly more complicated. In particular, since I have a closed form expression for the inversion, I know that the inversion will always be well behaved. I don't have numerical issues. It can't suddenly fold in on itself. If I'm doing some sort of like discretization where I discretize the flow by moving things along geodesics, although infinitesimally they won't fold over, since I'm taking a finite time step, there is numerical issues that can creep into here. So you have to be more careful. Excellent. All right, so we can center with respect to transformations that are characterized by gradients of functions in some functional space. What can't we center for? Transformations that are characterized by things that are not gradients of functions in some function space. That's not interesting. But let's make this concrete. Let's take a look at Mobius transformations, right? So what do we say? We said, to talk about Mobius transformations, we were looking at inversions. Those correspond to gradients of linear functions. Right? Now, linear functions are nice. They are sort of the smoothest space of functions on the sphere that don't have constant functions. And so the gradients of linear functions is, in some sense, the smoothest space of vector fields. Almost. What's missing? Well, if I have a vector field on a surface, an oriented surface, I can always rotate it by 90 degrees. Right? That I can do. And that, in some sense, is a vector field that is just as smooth as the one I started with. And these vector fields, the rotations of the gradients by 90 degrees, these are actually correspond exactly to rotations. This is the second half of the equation. These are not gradients of any function. By construction, they're divergence free. Right? So this vector field is curl free because it's the gradient of something. Its rotation by 90 degrees is going to have to be divergence-free, which is, of course, what rotations are. They preserve area. They can't compress area, so they're divergence-free. We can't express them as a gradient of anything, and indeed, this technique that we used for handling translations doesn't work for rotations. It gives us, so this goes back to the original question that I was sort of asking you, why are translations and rotations different? Infinitesimally, translations are curl-free. Rotations are divergence-free. If it's curl-free, assuming, yeah, that things are good. If it's divergence-free, you're in trouble. Okay. So let me run through what we do for rotations, although this is less interesting. This is sort of applying standard signal processing. Right? We had a shape. We had two shapes. We mapped it to the sphere. We did conformal parametrization. We even moved it so that the center of mass is at the origin. And now we'd like to find the rotation that best aligns these two spherical functions. So what are we going to do? We're going to do something naive. These spherical functions are, say, the conformal factors over the sphere. For every point on the sphere, we have conformal factors. We want to find the rotation that minimizes the L2 distance between these, or equivalently, the rotation that maximizes the correlation between these, the dot product. So what are we going to do? We're going to do standard signal processing. We have functions on a sphere. We're going to discretize them. This is probably not the cleanest way. How do you discretize them? Okay. Map the sphere. You can compute the spherical harmonics. You can get their frequency decomposition. And when you have functions on a circle and you want to correlate them, what do? You multiply the frequency components. You multiply the constants, the first order, the second order. You can do exactly the same thing. You're going to multiply out frequency components. But the difference here is that because rotations in 3 dimensions are not commutative, these spherical harmonics come in spaces that are, or frequency spaces are not one-dimensional. They're 2L plus 1 dimensional. So this is follows from Schur's law. Okay. So when you're doing the multiplication, you actually have to cross multiply. So you multiply the 0th frequency times the 0th frequency, all the things in the first frequency times the first frequency, all the things in the first frequency, all the things in the second frequency. Second frequency, right? So you'll get 1 0th order term, 9 first order, 25 second order, and so on. These are the coefficients of a function expressed in terms of the Fourier decomposition over SO3, the group of rotations. We start off spherical harmonics were over S2. The product of these guys is over SO3. These are sometimes called the Wigner D functions. You want to go from the expression in terms of the Fourier coefficients into actual discrete values on SO3, maybe in terms of discretely sampling the Euler angles. So you're going to run the inverse Fourier transform on SO3. That gives you a grid of values, a 3-dimensional grid of values for the 3 Euler angles. You walk through this grid, you find out where it's maximized. That gives you the angle maximizing the correlation. You apply it to your spherical function, and you get your alignment. Okay. Good. Good. All right. Good.
So why did you need to discretize?
Why do I need? Because I need to apply the FFT basically. So I need a discrete sampling, some sort of discrete sampling. And yes, there's going to be some problems. Spherical maps can compress, so you can't have really high frequency terms. So if you discretize with not enough frequency, you're going to lose something. So this is not perfect. So that's why I'm sort of waving my hands around this, but fine. It's a poor man's approximation.
Just so when once you have discretized, you compute your two spherical harmonic decomposition, but the algorithm is just on the spherical harmonic coefficients, right?
Mm-hmm.
Because you have a formula to
Yep.
use the Funke formula. That gives you, so you're using the formula that gives you the.
So you take the spherical harmonic coefficients, you cross multiply them, just like you do for 1D correlation. That gives you Wigner D coefficients, coefficients for a basis of functions on SO3. So it's a frequency decomposition. If you run the inverse transform, that gives you the actual values on discretized at the rotations, sort of sampled in rotation spaces, sampled in Euler angles. Once you have those, you can just iterate through this grid of correlation values, figure out which one is maximal, find the rotation that corresponds to that guy, and just apply it. Let's talk about 2 applications. One is a toy application, but it works. So I'll talk about that first to feel good. And the other one is the application we want to work, and it doesn't work. We'll talk about that later. So not long ago, there was this work by Argument and colleagues to try and find conformal mappings to the sphere. But conformal mappings to the sphere cause all sorts of distortions. So what they were looking for is actually something slightly different. Conformal mappings that take a surface, let's say this guy over here, something with disk topology, and map it to a tile on the sphere. And then there's some symmetry group on the sphere that I can apply to map this tile everywhere else. For closed again, either disk topology or genus-zero surfaces. If it's a genus-zero surface, I need to introduce a cut somewhere to actually turn it open, and that'll give me this thing over here is the image of the boundary of the cut. And they argue that this is useful, that you can have some less distorting mappings. This is guaranteed to be fold-over free, this they show. But since I'm not an applied math person, when I see non-convex minimization, I get scared. So I got scared. But this is, at the end of the day, computing a conformal parametrization. So the natural question is, can I use existing techniques that do conformal mapping to give me these mappings over the sphere with symmetry? So what's the idea? What do I want to do? I want to take this in, and I want to map it to, well, this is a curve to the circle with symmetry. Let's say I want it to have fourfold symmetry. How would I do this? The easiest thing to do is take my surface, make 4 copies of it, cut it open, and stitch it together. So this is like a fourfold covering of my surface. It still has the topology of a curve, but it's a fourfold covering. So it naturally has the fourfold symmetry built into this curve. And now I can apply conformal parametrization, and it takes me to the circles, and it gives me exactly the symmetry that I want.
So how many copies are you going to use for this sphere?
Depends on which symmetry group I'm interested in. So that's the question. So they're all according to the symmetry group, so let me give you an example.
Why is it called orbifold?
A spherical orbifold is, I think, it's a tiling. So you're given a symmetry group, and it's a tiling of the sphere with patches where you just apply the symmetry group, and that tiles the whole sphere. And there are other orbifolds. There's Euclidean orbifolds, there's hyperbolic orbifolds, depending on sort of the curvature of the surface you're trying to mount. So here is this surface. This is a mannequin. Turn off the lights. So it's a surface with boundary, and here it is. You can see it, right? And what I've done is I've taken this thing, right? It already has a boundary. I break up the boundary into 4 parts, and I glue 24 copies of this thing, because the symmetry group that I was looking at has, I think, 24 different copies, in the correct way, which is a pain to implement, but I hope you'll believe me that I could do it. And I lay it over here. And for those of you who have seen some graphics, what's going on over here, this speckling pattern, is I have 24 triangle meshes all sitting on top of each other. And there's sort of, when I render the thing that's closest, but since there's 24 copies, there are actually different things that are, like, which is closest is arbitrary. It's up to machine precision. Sometimes it's backward facing, sometimes it's inward facing. So you're getting slightly different colorations as one peeks out of the other. Okay. Now, what I'm going to do is I'm going to run exactly the thing that I showed you before, conformalized mean curvature filter. So here's the step, and you can see that these things, these heads, are starting to separate. And they're over here. Let's run this again. All right, they're really separating now. You can see them. Good. And I'm just going to run this for a little bit. And what we're going to get is we're going to get this genus-zero surface that's going to conformally map to the sphere. And here it is. It's evolving.
So you stitch them at the neck.
You have to stitch, but you have to stitch them carefully. Right? Yeah. So stitching is it's easy for when you're talking about a circle. There's only one way to stitch, but when you're talking about a sphere, how you stitch them together took some coding, right? And so here it is. First of all, you're noticing that it's not convergent, and that could be 2 issues. One could be numerical precision. One is that the conformal map you're getting is not actually unique. It's unique up to Mobius transformation, so it could be sort of searching around in this kernel and just coming up with different solutions, each of which is equally good. So here it is. Okay, so there's 2 problems. You can see that it's not exactly spherical, right? It kind of looks oblong. And let's turn off the lights again. If you look at Y, you can see that there is sort of discretization trouble that you're going to have. You're going to have these really awkward triangles. I think that's most of what's causing this, is just the numerics, the discretization. But this we can fix. We can just take all the points on sphere and just map them to just divide them through by their length. Now we have a spherical tile. There we go. Perfect. Now we have a spherical tile. Nonetheless, this is not a tiling. It is certainly clear that this is not some sort of element of the symmetry group of the sphere applied to this guy. Right? These are different shapes, different sizes. Why? Didn't we do everything right? Well, it turns out no. We got a conformal parametrization. The conformal parametrization is unique up to Mobius transformation. Now, Mobius transformation, partially rotation, so that preserves this symmetry structure, but some of it's inversion. And inversions don't have to preserve the size of these tiles. So what we can do is we can just apply our approach of centering to this mesh over here, and there you go. So just centered, you're running exactly that 6-line algorithm that you got before, and here's your orbital form. And here you can see the edges. You can see that these tiles are all the same. Good?
Couldn't you apply the constraint to start with as you move with the zero mean?
When you mean when you're applying the conformalized mean curve?
When you yeah.
That's so. Yes. Yeah. Let's say yes. Let's say yes. So this is a slow implementation. I actually have a faster implementation. So this is slow because I have 24 copies. I'm actually running conformalized mean curvature flow on something that's 24 times the size of what I started with. I could start off with just one thing, one tile, and implicitly say sort of across the boundary, the element of the symmetry group is what's going to define where it's going to really incorporate the symmetry group. And then I have the linear system that is 1/24th the size, and symmetries by construction. So that's, for the fast implementation, that's actually what we do. So correct, you can, and you should. It's faster, and it gives you what you want without any issues with it. All right, good. But what was our goal? Our goal to start with was the following. We want to establish correspondences. So let's say I have a target shape, and I have source shapes. What do I want to do? I want to take a point on the shape. Let's say, I don't know, point on the belly. I say, okay, this maps to a point on the sphere. Let's see where that point is on the sphere, over here. What point that maps to on the target. Right, that should give me a mapping between my two surfaces. And here you go, here's what I got. Right, so this is the mapping of this guy to that target. And this is a mapping of this guy to that target. Right? They sort of have the same shape over here, but this is not a good map. If you look at something like the head, it's going sort of where it needs to go. It's sort of going towards the shoulders, but it's not going quite to the head of the target. Why? Well, to understand this, let's take a look at what's going on in the head. Right? Let's zero in on that area on the sphere, and here it is over here. Right? And what we're seeing is that where the head goes on the mapping on the sphere after alignment, they're not actually perfectly registered. Right? This guy's a little higher than this guy's a little lower, this guy's a little off and to the right. Right? So naturally, when I take this guy over here, the map it, it's going to pick up some point on the back. I'm going to miss. Why is this happening? Didn't we say that you should get the same conformal parametrization? So the answer is no. We said you get the same conformal parametrization if the shapes differ by a rigid, by an isometry. So not a rigid deformation, but by an isometry. Now, in this case, I have to have an actual ground truth mapping correspondences between this guy and this guy. So I can look at the deformation. How are the triangles deforming as I'm going from this guy to this guy? And I can draw in blue the extent of the lack of isometry, how much stretch and scaling there is. And you see that there is some. So as I move my hand up and down, there's going to be some stretching of the skin around the shoulder. As I lean forward or lean back, there's stretching of the skin around the stomach. Right? Same thing goes for where the legs are. And so I have these deformations that are not isometric. They're small. They're reasonably small, but they're there. And so the thing is, so they're small, so they're going to introduce small errors. But when I have things that are mapped to really tiny regions on the sphere, even a slight offset is going to result in a complete mismatch. If these shapes are, like the head, are mapped to a tiny location over here, even if I move them just a little bit down, it's going to totally mismatch where I want.
Yeah. So another question. So between these two examples, if you have a different mesh from the two things, you are doing like closest point on the two spheres because you have two spheres with different.
Anyway, I'm doing closest point. In any case, right? Because these vertices are not one-to-one correspondences on the sphere. So these are this guy and this guy are two completely different triangulations of the sphere. They happen to have the same number of triangles and vertices, but that doesn't make a difference. I will figure out where this lies on the sphere, figure out which triangle lives above it, and then do barocentric interpolation to figure out where it is on that surface. So, good. I got 2 minutes, which is really all I need. So there we go. Mobius transformation, we're looking at inversions and rotations. Inversions, those correspond to motions along curl-free vector fields, along the gradients of functions on the sphere, which means you can normalize for them canonically. You can do this on a per-shape basis, just like with translations, what we started with. Rotations, they correspond to divergence-free vector fields, right? They can't be the gradient of anything. You can't canonically normalize. That's not the contrapositive. But it's not obvious that you can canonically normalize. Certainly this technique will not extend to them. It is hard, and we know why it's hard. Luckily, in this case, we have fast signal processing techniques to solve this efficiently. Now, because of sort of the general approach that we did, you don't have to just look at linear functions on the sphere. You can look at higher order harmonics. In fact, you don't even have to look at the sphere at all. You could look at normalizing signals on other geometries, compute the Laplace autonomy operator on that geometry, figure out, do a spectral decomposition, get the lowest eigenvectors, and do deformations with respect to the gradients of those. It doesn't have to be genus-zero. The one problem with non-genus-zero surfaces is that you have vector fields that are very smooth, as you want, completely curl-free, but also completely divergence-free. Right? And so they're sort of these smooth transformations that are not gradients of anything that you just can't capture. Good. So trivial to implement. We understand rotational alignment. Theory is nice. I hope I've convinced you. But you can't just say conformal parametrizations in the context of nearly isometric. Since it's nearly isometric, you're pretty close to being done. Nearly isometric can actually be a big problem in the context of conformal deformations. Good. Thank you.
Just one question.
Yeah.
It comes in two components. First component is what do we do with discrete objects if we want to translate these results? And the second component is there a similar theoretical setting for things that are higher dimensional? These are not surfaces.
So everything here was discrete to start with. All the computations were discrete. So is that?
The original surface, you considered that it was a Riemann surface, yes?
Well, I mean, really everything here is triangle meshes. Absolutely everything throughout. Starting with the first bunny that we saw.
Sure, that addresses my first question.
And the answer is yes. A priori, there is nothing about this that has to do with the fact that you're on the surface. In fact, we didn't use anything. We just used function spaces on some domain. Gradients of those function spaces define deformations. The results about centering, about things being symmetric causes definite whole. The only thing that you probably need to use you just need a compact manifold so you can actually do your integration. That's it. Yes?
I have a question. So you said when f is the linear function, that's the first order spherical harmonics.
Mm-hmm.
By first order spherical harmonics, you mean y1 functions. Is that, if I understand?
Yeah, exactly. So if you
so
restrict,
y1's are linear in which variable?
so if you look at the y1 functions in terms of the x, y, and z components, then they're linear in terms of the x, y, and z components of the points on the sphere. If you look at them in terms of the spherical coordinates, in terms of theta and phi, of course they're not linear. Then they're trigonometric functions.
But if
you're looking at them as
if you write them in terms of x, y, z, you will get root over x square plus y square plus z square in the denominators. You will get the radius in the denominators.
the radius was 1. We're on the sphere. If you're looking at the spherical harmonics, volumetric spherical harmonics, that's a different question. But on the sphere, there's no square roots. It's just linear.
Just one last question. For the rotation normalization, I guess
Rotational alignment. We can't normalize.
Yeah,
the whole point is we can't.
So there you use again the conformal ratio, I guess. But you could have used maybe if you use a curvature, for example.
You can use that. It's not. This is sort of I wave my hands around because I mean, at the end of the day, what you really want is you want some notion of distance between surfaces, some notion of a metric, and then you're showing that you're minimizing that. We're not doing that. Right? So you might want to say overall bijections that preserve area. This minimizes the sum of square distances, integrated sum of square distances. But we don't have a nice formulation. And there is a question of whether there's sort of an optical flow formulation of what the optimal transformation is and showing that this minimizes that. But certainly, there might be a chance for the inversion normalization, because that seems solid, but the rotation normalization, certainly just using the conformal factors happens to be a signal we have. We could have used any other intrinsic signal, including curvature. The only slight nuance I think about this is that the signal is actually a 2 form, it's not a 0 form. And so the conformal factors are fundamentally 2 forms. We talk about the ratio of areas. But you can turn anything from a 0 form to a 1 form. And so that's not really.
Yeah, so we have some refreshment next door.
Everybody sign?